When you hear people say beyond the moon, you probably think, okay, that means a slightly bigger version of Apollo. A longer loop, a bit more distance, same basic idea. That picture is already out of date. If you keep thinking like that, you totally miss how hard the real next step is. Let's pin down what beyond the moon actually means in hard numbers. The average distance from Earth to the moon is about 384,400 kilometers, roughly 239,000 miles. Light takes about 1.3 seconds to go one way. That whole region, Earth plus the moon and the space around them, is the Earth-Moon system. In this video, beyond the moon does not mean slightly past 384,400 kilometers, then turn around and fall back to Earth. It means something much tougher. Humans crossing roughly that 400,000 kilometer radius and then staying out, in a path where the sun is the main gravitational boss, not Earth. In plain language, you're not just doing a big loop that happens to go by the moon, you're leaving Earth's local neighborhood and letting your ship fall around the sun instead. Once you do that and you don't immediately swing back, you're in true deep space. Your orbit is heliocentric, sun-centered, not Earth-centered. That is a totally different game for navigation, for life support, for risk. So if that's the real line, the obvious question is, how close have we come to it with actual human beings on board? Right now, the human distance record is still frozen in time back in 1970. It belongs to the crew of Apollo 13. During that mission, after the oxygen tank exploded and the landing was cancelled, the spacecraft was put on a free return trajectory around the moon. At its farthest point, the crew reached about 401,000 kilometers from Earth, around 249,000 miles. That is, to this day, the farthest any person has ever been from Earth. But look at that number carefully. The average Earth-Moon distance is about 384,400 kilometers. Apollo 13 only went roughly 4% farther than that. In simple terms, we barely pushed past the moon's orbit. If you treat the Earth-Moon gap as one full unit of distance, Apollo 13 added a tiny bit on top, not an order of magnitude. Technically it's a record, yes. In terms of interplanetary scale, it's still very much local. So then you might say, fine, humans haven't gone that far, but our hardware has. Surely something designed for humans has gone way beyond that by now, right? The first real step up was Artemis 1. In 2022, NASA launched the uncrewed Orion spacecraft on a deep space test flight. Orion is built to carry astronauts in the future. On Artemis 1, it flew a distant retrograde orbit around the moon and reached a maximum distance of about 432,000 kilometers from Earth, roughly 268,563 miles. At that farthest point, it was about 69,000 kilometers or 43,000 miles beyond the far side of the moon. That matters. Orion is not a lightweight probe. It has a human-rated heat shield, a habitable cabin, life support systems, and all the safety margins that go with that. Proving that such a vehicle can survive weeks in deep space, handle high-speed re-entry, and operate reliably that far out is a big deal. It shows that, on the engineering side, we can operate human-class spacecraft beyond the immediate lunar environment. But here's the limitation. Even at that record distance, Orion was still gravitationally near Earth. It was still moving in a complex orbit tied to the Earth-Moon system, not cruising freely around the Sun, left low Earth orbit, yes, but it did not truly leave Earth's gravitational neighborhood the way a Mars-bound spacecraft must. The mission stretched our comfort zone, but it did not cross that deeper border. So now you have to ask a harder question. If that kind of mission still counts as local, what does far really look like when you start talking about Mars and true interplanetary travel? The scale jump is brutal. The moon, on average, sits at about 384,400 kilometers from Earth. Mars is on a totally different level. At its closest, during a good alignment, Mars can come to about 54 million kilometers away from Earth, around 33 million miles. At its farthest, when the planets are on opposite sides of the Sun, the distance can stretch past 400 million kilometers, around 250 million miles, And when you design a full mission profile, the total path your ship travels, out and back, ends up on the order of 1 billion miles. So here's the cold reality. The Apollo 13 distance record, around 401,000 kilometers, is tiny compared to even a short Earth-Mars distance. You could line up hundreds of Earth-Moon gaps end to end just to match a single good Mars separation. When people casually say, or we went to the moon, Mars is just the next step, they're ignoring the sheer size difference. Mars makes the moon look local, like a nearby suburb. That means when you ask, when will humans go beyond the moon, you're actually asking something much more ambitious than it sounds. You're asking, when do we take the first step onto interplanetary scales, where distances and travel times are big enough that you cannot treat it as a longer Apollo mission, you have to design around a completely different level of risk. So we need a clear rule for when we're allowed to say, honestly, we did it. No. We finally went beyond the moon without cheating and just pointing at a slightly bigger loop. For this story, the bar is high on purpose. Finally beyond the moon means humans spending significant time outside the Earth-Moon system. That could be a Mars flyby where you don't even enter orbit. You just swing past the planet and your path around the sun naturally carries you back to Earth. It could be a Mars orbit mission where you never land, but you stay in orbit for weeks or months, controlling robots and taking measurements. It could be a deep space asteroid mission, where your spacecraft's path is a long, stretched-out orbit around the sun that takes you far beyond the moon and keeps you there. The key features are not just distance, they're exposure and commitment. You're weeks or months away from any realistic chance of coming home quickly. There is no 3-day emergency burn like Apollo. Communications delays are not 1.3 seconds one way. They can be several minutes, even over 20 minutes. Resupply is effectively impossible. Every system, life support, power, communications, navigation, medical care, has to work for a mission length of years, not months, with no rescue waiting close by, or that's why this definition matters. Once you accept it, you see that we haven't done anything like this with people yet. We've lived in low Earth orbit. We've done short trips to the moon. We've sent uncrewed hardware far out. But we have not yet put a crew in a heliocentric orbit that leaves the Earth-Moon system and stays out there. So now the real tension starts to build, because the next question is very simple and very uncomfortable. If this is what beyond the moon really means, how far have we actually gone, step by step, from low Earth orbit up to the edge of this boundary, and how small does that progress look compared to where we say we want to go? Here's the blunt truth. When you zoom out and look at all of human spaceflight, we have basically just been running in circles right above our own planet, with a few short dashes to the moon more than 50 years ago. And then, nothing farther since. Right now, almost everything we do with people in space happens in low Earth orbit, LEO. A shell only about 400 to 420 kilometers above the surface, roughly 250 to 260 miles. The International Space Station lives there, looping around Earth at about 400 kilometers altitude, moving at about 7.8 kilometers per second, roughly 28,000 kilometers per hour, about 17,500 miles per hour. That speed means it laps the planet about 16 times every day. To you on the ground, that sounds insane. To orbital mechanics, this is just the basic minimum speed you need to not fall back down. So the shocking part is, as extreme as that sounds, it's still very close to home. At 400 kilometers up, you're only a tiny fraction of the way to the moon. You're skimming the skin of Earth's gravity well, not climbing out of it. That's why LEO is like a hamster wheel, lots of motion, lots of speed, but you never actually leave the cage. You go around and around and around, but in terms of distance from Earth, you barely move. So then the next question is, when did we actually break out of that hamster wheel? And how far did we really push it? The only time humans have gone significantly beyond low Earth orbit was the Apollo era, between 1968 and 1972. Those missions didn't just stay in LEO, they lit the third stage and went on what's called a translunar trajectory, a path that takes you out to the moon's distance. Apollo 8, 10, 11, 12, 13, 14, 15, 16, 17, All of them followed some version of that playbook. Most of those crews reached distances in the range of about 370,000 to 400,000 kilometers from Earth. That's roughly 230,000 to 250,000 miles. Apollo 13 still holds the record. When the crew had to abort the landing and loop around the far side of the moon, their path carried them to about 401,000 kilometers from Earth, around 249,000 miles. That's the number you hear over and over, because it's still the farthest humans have ever gone. And remember, that record is only a few percent beyond the average Earth-Moon distance. It's impressive compared to LEO, but compared to interplanetary space, it's still very modest. Then the obvious problem shows up if Apollo was half a century ago, and we keep saying we're going back and going further. What have we actually done since then that pushes that boundary, even with no one on board? The first real modern move was Artemis 1 in 2022. This time the spacecraft was Orion, a capsule built and tested to carry astronauts in deep space. On Artemis 1 there were no people inside, but the systems, the layout, the heat shield, all of that was human-class hardware. Orion flew into what's called a distant retrograde orbit around the Moon. In that trajectory, it looped as far as about 432,000 kilometers from Earth, roughly 268,563 miles. At its farthest point, it was around 69,000 kilometers, about 43,000 miles beyond the Moon's far side. This is important because we finally took something designed for humans and pushed it tens of thousands of kilometers past anything Apollo ever did. The mission proved that Orion could cruise in deep space for over 3 weeks, handle the cold, the radiation, the navigation challenges, then slam back into Earth's atmosphere at around 11 kilometers per second, about 25,000 miles per hour, and survive. But even with that success, there's a limit you can't ignore. Dynamically, in terms of gravity and orbital energy, Artemis 1 was still operating in Earth's neighbourhood. The spacecraft was following a path that mathematically is more complex than a simple circle, but it was still part of the Earth-Moon system. It wasn't a free, clean orbit around the Sun like a Mars mission would fly. It was a rehearsal, not the full performance. So that naturally leads to the next step. When do we finally put humans back on a path that pushes the record? Not just with hardware, but with actual people. That's where Artemis 2 comes in. The plan for Artemis 2 is to launch 4 astronauts on a roughly 10-day mission. They'll ride Orion on a free return path around the Moon, meaning the trajectory is designed so that even if the engines failed after the big burn, the spacecraft would still loop around the Moon and fall back to Earth. On that path, they're expected to reach about 7,600 kilometers beyond the lunar far side, around 4,700 miles past it. That should push the human distance record slightly beyond Apollo 13's 401,000 kilometers. You can think of Artemis 2 as the last big test lap with people on board, before we talk about anything more ambitious. It checks the boxes for life support in deep space, human factors over about 10 days outside LEO, navigation and comms at lunar distances, and it shows that the heat shield and re-entry profile work not just on paper or with sensors, but with a real crew depending on them. But even if Artemis 2 flies perfectly and sets a new record, you still have to face one more hard fact, and this is where the tension really spikes, because the gap between that mission and true beyond the Moon is bigger than most people realise. Here's what we have not done yet. No human being has ever flown in a true heliocentric orbit, a path where the primary thing you are orbiting is the Sun, not Earth. No person has ever been more than about 0.001 astronomical units from Earth. That's about 150,000 kilometers, in the sense of being in a trajectory that keeps them out there for long. Every crewed mission in history, from Vostok to Apollo to the ISS to Crew Dragon, has been, at most, about 3 days away from a powered return to Earth. If something goes wrong, you light the engines, you aim at home, and you're back in a matter of days, not months or years. That's the wall we have to break. Beyond the Moon, in the strict sense we're using, means going past that 3-day safety buffer. It means a mission where once you commit to the transfer burn, you cannot just change your mind and head home quickly. you are locked into a path that will keep you far from Earth for a very long time. That's the psychological wall, the engineering wall, all at once. So now you see the pattern. We orbit low, close to Earth, almost all the time. We did 6 fast dashes to the moon decades ago, and 1 emergency loop that set a distance record no one has broken with a crew. We flew 1 uncrewed test that finally pushed human-rated hardware a bit farther. We are planning 1 more crewed lap that might nudge the record again. And then, there is a huge empty space between that and the first real interplanetary flight. The next question is brutal but necessary. If going beyond the moon means breaking that wall, what does the physics bill look like in terms of speed and energy? And why is it so much harder to escape Earth entirely than to just sit in low orbit or do a quick lunar loop? You might think that going from low Earth orbit to deep space is just a case of press the gas a bit more, but the numbers are much harsher than that. And this is where the dream of going beyond the moon runs straight into the physics bill. Start with the basics. Just sitting in low Earth orbit already means you're going insanely fast. At about 400 kilometers up, to stay in orbit and not fall back, you need roughly 7.8 kilometers per second of sideways speed. That's about 28,000 kilometers per hour, around 17,500 miles per hour. At that speed, you're in free fall. You're constantly falling toward Earth, but you miss the ground because the curve of the planet drops away beneath you. That's orbit. Now compare that to what you need to actually get out of Earth's grip. To fully escape Earth's gravity, the ideal speed at the surface is about 11.2 kilometers per second. That's around 40% faster than 7.8. And 40% doesn't sound insane, right? It sounds like going from 100 to 140 on a highway. But here's the catch. Kinetic energy goes with the square of speed. So when you bump the speed from 7.8 to something closer to escape, you're almost doubling the energy per kilogram. In other words, every kilogram of spacecraft, fuel, metal and human suddenly costs nearly twice as much energy to push toward freedom compared to just parking in low Earth orbit. So now you see the first trap, sitting in orbit, is already hard, but escaping Earth entirely is way harder than it looks from the speed numbers alone. And remember, that's just to leave Earth's gravity well. That doesn't get you to Mars yet. So what happens when you stack Mars on top of that? From the launch pad to low Earth orbit, the total speed change you have to buy, counting gravity losses and drag, is on the order of 9.4 kilometers per second. Your rocket burns through stages, dumps empty tanks, and finally drops you into that 7.8 kilometer per second orbital path. At that moment, a lot of people think, okay, we're basically halfway, right? Not really. From that orbit to hop onto a standard transfer path to Mars, a Hohmann transfer, you need roughly another 3.6 kilometers per second of delta V, that is, extra change in velocity. So the ladder looks like this. You buy it about 9.4 kilometers per second just to reach orbit, then you have to pay another 3.6 on top to go interplanetary. That extra burn doesn't sound huge in speed terms, but remember, any fuel you use for that second burn has to be carried all the way up from the ground during the first burn. That's the second trap. Your rocket is not just lifting the crew and the habitat, it's also lifting a second mountain of propellant that you won't use until you're already in space. So the whole stack explodes in size, just because you want that extra few kilometers per second at the top of the climb. And that brings us straight into the heart of the problem, the rocket equation. Chemical rockets, the kind we actually fly, throw exhaust out the back at speeds of around 3 to 4.5 kilometers per second. That number, the exhaust velocity, sets the scale for how efficient your rocket can be. The Tsiolkovsky rocket equation in words says this: if you want more and more total speed change out of a rocket with a given exhaust velocity, the fraction of your starting mass that must be propellant goes up exponentially. Not linearly, not gently, but brutally fast. So if you say, I want to launch from Earth's surface and go all the way to Mars on one big rocket, with no refueling, the math responds by handing you a ridiculous design. Hundreds of tons of propellant at the bottom to deliver maybe a few tens of tons of actual useful payload and habitat at the top. In practical terms, you end up stacking giant stages on giant stages, just so that a tiny fraction of the original mass is still there by the time you're in deep space. That's why early concept art for Mars ships looks like skyscrapers lying on their side. The structure exists mostly to hold propellant, not people. This is the tyranny part. You can't argue with the rocket equation. You can only choose how you pay the price. Bigger launch vehicles, more launches and refueling, or higher performance propulsion. This is where the monsters come in. NASA's Space Launch System, SLS, is built to brute force that lower part of the problem. At liftoff, SLS Block 1 pushes about 8.8 million pounds of thrust, roughly 39 meganewtons. Later versions climb even higher. Depending on the configuration, it can send something like 26 to 45 metric tons toward the moon. That's roughly 57,000 to 99,000 pounds. If you want a mental picture, that's in the ballpark of hurling a fully loaded semi-truck not just into orbit, but onto a path that heads toward the lunar region. SpaceX's Starship targets a different angle. The goal is over 100 metric tons to low Earth orbit, fully reusable, with the idea that you launch many tanker flights to refill one Starship in orbit, then that vehicle leaves for the Moon or Mars. So instead of one giant expendable rocket, you get a system that tries to spread the rocket equation pain across multiple launches and reuse. But notice something important here. The physics bill doesn't go away. Whether it's SLS or Starship, you are still paying that exponential mass tax. You either build very big, you refuel in orbit, or realistically you do both. There is no free shortcut. So you can see the pattern forming. Just to get a human habitat and its life support far beyond the moon, the rockets have to be enormous, the fuel loads are staggering, and every extra kilometre per second you need hits your design like a hammer. Still, you might say, if we're willing to build huge rockets and launch them often, isn't that just an engineering and budget problem? Why do people keep talking about windows and alignments, like some horoscope for rockets? Here's why timing matters so much. Earth and Mars both orbit the Sun, but they don't move together. Sometimes Mars is on the same side of the Sun as Earth, relatively close. Sometimes it's on the far side, very far away. The most efficient path, the classic transfer orbit, only lines up properly when the positions of Earth and Mars are just right. That happens roughly every 26 months. If you launch in that window, you can reach Mars with that roughly 3.6 kilometers per second push from low Earth orbit. If you miss it, you have two bad choices. One, you spend significantly more delta Vs to force a less efficient path, which means even more propellant, even bigger rockets, and maybe a mission that becomes too heavy and too expensive. Or two, you accept much longer trip times on trickier trajectories, which means more time in deep space, more radiation, more wear on life support, and more psychological stress on the crew. So when you ask, when will humans finally go beyond the moon? You're not only asking about technology, you're also asking about orbital mechanics. Even if the rockets are ready, you still have to hit a series of moving planetary targets on a schedule set by the solar system itself. You cannot vote away the 26-month launch cycle. You either line your program up with those windows or you wait. And here's the key tension. Even if you accept the rocket equation, even if you build the heavy lifters, even if you time your launch perfectly, you are still sending fragile human bodies into a place with higher radiation, no gravity, and no quick way home. So the next hard question becomes, once you've paid the physics bill to get beyond the moon, what is deep space itself going to do to your crew, and can their bodies survive the trip without falling apart? Here's the part nobody likes to think about. Even if you solve the rocket problem, deep space itself is dangerous in a way low Earth orbit just isn't, and the further you go beyond the moon, the more that starts to dominate your timeline. Start with radiation. In low Earth orbit, like on the ISS, you're still tucked inside most of Earth's magnetic bubble. That field deflects a big chunk of the high-energy particles flying around the solar system. Even with that protection, astronauts on the station see on the order of 0.5 to 1.0 millisievert of radiation per day. You can think of a millisievert as a unit that measures how much biological damage the radiation can do, not just how much energy hits you. Now take away Earth's shield. Measurements from deep space probes and from instruments on Mars missions show that once you're out between the planets, or sitting on Mars' surface with only a thin atmosphere above you. Daily doses cluster somewhere between about 0.5 and 2.0 millisieverts per day, depending on how active the sun is. So roughly speaking, the worst days out there can be a few times harsher than a typical day on the ISS. Stretch that out over the length of a real Mars mission. A credible there and back timeline, including travel plus time in Mars orbit or on the ground, is around 900 days. Multiply those daily doses by that many days, and you end up with a total in the ballpark of 0.5 to 1 sievert. 1 sievert is 1,000 millisieverts. That's not instant death, but it is firmly in the zone where your lifetime cancer risk gets a noticeable bump. People often compare it to getting multiple full-body CT scans every single month for years. That's not a shrug it off level anymore. That's a we need to justify this very carefully level. So that's the slow background problem. But you might be wondering, is that the whole story, just a steady drizzle of radiation you can plan around? Not really, because deep space throws two very different types of radiation at you, and one of them doesn't care about your schedule at all. First, there are galactic cosmic rays, GCRs. These are high-energy particles, mostly protons but also heavy atomic nuclei that come from outside the solar system. In deep space, they can deliver something like 0.1 to 0.2 gray per year. A gray is a measure of energy deposited in tissue. That doesn't sound huge, but the problem is the quality of that dose. Some of those particles are heavy ions moving so fast they behave like microscopic bullets, punching straight through metal and through your cells, leaving dense damage tracks that are hard for your body to repair. Second, there are solar energetic particle events, SEP events, tied to solar flares and coronal mass ejections. These are more like random spikes. For months, nothing extreme happens. Then the sun burps out a storm of particles, mostly protons, that race outward. If your crew is unlucky and unshielded, they can take a dangerous dose in a matter of hours. In the worst case, that's acute radiation sickness territory. So you have this nasty combination: a chronic, always-on drizzle from galactic cosmic rays, plus occasional blast furnace bursts from the sun. That double hit is why deep space mission design can't just say add some shielding and move on. Heavy shielding helps with solar storms, but beyond a certain point it doesn't help as much with galactic cosmic rays, because some of those heavy ions generate secondary radiation when they smash into your shielding. So now you're playing a trade-off game where more mass doesn't always equal more safety, and all of that is just what the radiation does. Your body has another problem in deep space, and this one kicks in as soon as the engine's cut off and you're weightless. In microgravity, your body quietly starts unlearning how to be a human that lives in 1G. On the ISS, unless astronauts use very aggressive countermeasures, they lose about 1 to 2% of their bone density every month. Muscles, especially in the legs and back, weaken. The cardiovascular system deconditions because your heart no longer has to fight gravity to pump blood up from your legs. Fluids shift toward your head, which can mess with your vision. Over a typical 6-month ISS stay, all of this is manageable, but only with strict exercise routines and medical monitoring. We know single missions close to a year are survivable. One NASA astronaut spent 355 days in orbit. Another record-holding woman spent 328 days. They came back, they recovered, they're okay. But that data set is still short, and those missions were heavily supported, with constant medical oversight, resupply, and the knowledge that in a worst-case scenario, a ride home was days away, not years. It proves we can endure, once for about a year. It doesn't prove that doing that repeatedly or stretching it to 900 days in a harsher radiation environment is safe. So now connect this with the timeline. You might ask, if we can handle a year in orbit, aren't we basically ready for Mars? A minimum energy Mars trip with current chemical propulsion is around 6 to 9 months one way. You don't just turn around immediately. You either stay in Mars orbit or on the surface for a while, then you wait for the next favourable alignment to come back, which is more months. Put that together and you're looking at something like 2 to 3 years outside low Earth orbit, with no quick return option. That's 2 to 3 times longer than our longest continuous stays in orbit, plus a harsher radiation environment the entire way. Until we can show with numbers that we know how to keep a crew physically and medically stable over that entire time, missions beyond the moon are not just brave, they're scientifically uncertain. You're betting on how human biology will react to a combined load of radiation, microgravity, isolation and stress over a timescale we have never directly tested. So what do? Just accept the risk or start changing the hardware and the mission plans so your crew isn't walking into a slow-motion health disaster? There are a few main tools on the table. For radiation, you can build storm shelters inside the spacecraft, small zones lined with hydrogen-rich materials like water or polyethylene, where the crew can hide during a solar storm. You can store water tanks and food around crew quarters, using the stuff you have to carry anyway as extra shielding. For galactic cosmic rays, you look at overall layout, how much mass you can pack around living spaces without making the ship too heavy to launch. For microgravity, one big idea is partial gravity using rotation. You can spin part of the spacecraft or link two modules with a long tether and rotate them like a dumbbell to create artificial gravity by centrifugal force. Maybe you don't get a full 1G, maybe you aim for Mars gravity, about 0.38 GG, and see how much that helps with bones and muscles. People are also studying onboard centrifuges that the crew can strap into for a few hours a day, like a spinning gym session. You can also play a timing game with the sun. During solar maximum, when the sun is more active, you get more solar storms, which are dangerous but somewhat predictable, and at the same time, the overall flux of galactic cosmic rays actually drops because the stronger solar magnetic field deflects more of them. Some mission planners argue that launching during solar maximum with good storm shelter designs and warning systems might be safer overall than going during quiet periods when GCRs are higher. Here's the key point. These are not just technical details for PowerPoint slides. Every kilogram of water you choose to put into shielding, every decision to add a rotating section, every choice about when in the solar cycle you launch, directly shifts the date when a beyond the moon mission becomes responsible instead of reckless. And that leads straight into the next pressure point, because now the question isn't just, can we keep people alive out there? It becomes, what ships are we actually building to carry them through that environment? How big are they? How often can they fly? And which design bets are we really making with our first deep space cruise? Here's the uncomfortable question you have to face now if we really want to send humans beyond the moon. What actual ships do we have on the table today? Not in science fiction, not in concept art, but in steel and fuel and flight history. Start with the government workhorse. NASA's Space Launch System, SLS, is built as a brute force moon truck. In its current Block 1 version, it can push more than 26 metric tons onto a path toward the moon. The planned Block 1B upgrades that to around 42 to 45 metric tons. At liftoff, you're talking about roughly 8.8 to 9.5 million pounds of thrust, which is about 39 to 42 meganewtons. That puts it in the same club as the most powerful rockets ever flown. Translated into normal terms, every time you light SLS, you can send something like the mass of a small 2-story house, fully packed on a one-way trip past the moon. Not a probe, not a CubeSat, a serious chunk of hardware. The trade is that SLS is expensive and rare. You're not going to see dozens of these launches per year. It's designed as a national flagship rocket, not a rapidly reusable transport system. So you end up with a paradox. SLS is incredibly capable per launch, but the launch cadence is slow and the cost per flight is huge. That's fine for a few Artemis missions, but if your plan for going beyond the moon depends entirely on SLS, you're betting on a small number of very high-stakes shots, each one carrying a big percentage of your total program. Now look at what SLS is actually throwing out there. The crew rides in Orion, NASA's deep space capsule. Orion has already done a real deep space mission on Artemis 1, spending about 25.5 days beyond low Earth orbit. It went around the moon in that distant retrograde orbit, then came barreling back toward Earth at around 11 kilometers per second, roughly 25,000 miles per hour. During re-entry, the heat shield saw temperatures near 5,000 degrees Fahrenheit, about 2,760 degrees Celsius. That test was a success in the big picture sense. The The capsule stayed intact, the avionics worked, the trajectory was precise. But when engineers inspected the heat shield, they found something they didn't fully predict. There was unexpected chipping and extra char, over 100 spots where the AV-coat material had eroded more than the model said it should. NASA's analysis so far leans toward handling this with changes to the re-entry profile and trajectory, rather than ripping out and redesigning the whole shield. For you, as someone thinking about Mars-class distances, that raises a sharp question. Not, can Orion survive one lunar mission? But, do we trust this system for multiple deep space flights, with crews on board, at distances where there is zero room for surprises? It's not a showstopper, but it's a reminder that even the proven hardware still has unknowns, and unknowns are what you want to minimize before you send people hundreds of millions of kilometers away. On the other side of the table, you have SpaceX's Starship, which is almost the opposite philosophy. Instead of a few rare, ultra-expensive launches, Starship is aiming for a huge, fully reusable system that can fly often. The target payload is on the order of 100 to 150 metric tons to low Earth orbit in a single shot. The idea is that you launch one Starship that will go to the Moon or Mars, and then you launch multiple tanker Starships to refuel it in orbit, filling it up with the propellant it needs for the deep space burn. Starship has already flown several integrated test flights with the booster and the upper stage. Some milestones have been hit, like reaching space, completing partial flight profiles and testing re-entry. But multiple upper stages have ended their flights in rapid, unscheduled disassembly, meaning they broke apart or exploded before a controlled landing. That's not a secret, that's expected in this kind of fast iterating test program. It also means the vehicle is still early in its development curve. It is not yet a trusted people carrier. Right now, Starship is a promise, not a finished product. So put those two pictures side by side. On one side you have SLS and Orion, a conservative, heavily checked government system, extremely powerful, extremely expensive, flying rarely. On the other you have Starship, a private mega-rocket aiming for frequent flights, huge mass to orbit, in-orbit refueling and long-term explicit Mars ambitions, but still working through major test failures. The key question is, how do these two very different approaches actually map onto the first missions that go truly beyond the Moon? In the near term, SLS plus Orion is the backbone for Artemis. For a beyond the Moon style mission, SLS is good at one thing, throwing heavy, high-value payloads out of low Earth orbit in one shot. That fits well with multi-launch architectures. You launch a large habitat module or a propulsion stage on one SLS, maybe send it to lunar orbit or to a gateway station in a special orbit near the Moon. Then you launch a second SLS with Orion and the crew. They rendezvous with the waiting habitat or transfer stage, dock, and then that combined stack heads further out. This way, SLS and Orion don't have to do everything at once. Instead of one giant Mars ship, you break the mission up. One launch for living space, one for crew, maybe others for cargo. It's slow, complex, and expensive, but it's grounded in capabilities that are already flying or close to flying. Starship changes that picture if it hits its design goals. With over 100 tons to low Earth orbit and an in-orbit refueling system, you could, in principle, launch a Starship configured as a Mars cargo ship, refill it with tanker flights, and send tens of tons of supplies and hardware to Mars in one go. If the economics work out anywhere near what SpaceX talks about, on the order of $100 million per metric ton delivered to the Martian surface, that is actually cheap on interplanetary scales. If that happens, you can afford to send multiple uncrewed Starship flights ahead of the first crewed mission. You can pre-position habitats, power systems, return vehicles, and spare parts on Mars or in Mars orbit. Each one is a dress rehearsal for the deep space flight profile. You gather real data about radiation, dust, landing dynamics, abort options. That kind of rapid, repeated, uncrewed testing would pull the ready date for human missions forward, because you're not guessing from simulations, you're learning from real hardware that has already run the route. Of course, that all depends on Starship actually reaching reliable reusability and high flight rates. If it stays stuck in the prototype stage, SLS and Orion carry more of the load. If Starship matures fast, SLS becomes the slow, high-reliability backbone, and Starship becomes the high-volume freight train. So right now, you can honestly say this. We have two very different bets on the table. One is a government super rocket that flies rarely, but is built to be as predictable as possible. The other is a private mega rocket that aims to fly often, maybe dozens or hundreds of times, but is still blowing up during tests as it climbs the learning curve. Whichever one proves itself first, or whichever combination of the two we actually lean on, that's the hardware that will carry the first humans beyond the moon for real. And that sets up the next problem. Because once you have these huge rockets and deep space capsules, you still need somewhere for the crew to live for 2 to 3 years straight. The rocket is just the elevator. The real question becomes, what kind of habitat and life support system can keep a small group of humans alive, mostly closed loop for 900 days or more, far from Earth, with no resupply and no rescue? Here's the part that sneaks up on people. The rocket gets all the attention, but for a mission beyond the moon, the real problem is turning a metal tube into a place where a handful of humans can actually live for years without a steady lifeline from Earth. Start with what we've already proven. Since November 2000, the International Space Station has been continuously inhabited. That's over 25 years, more than 9,000 days of humans living off-world, orbiting at about 400 kilometers, around 250 miles above your head. The ISS is not some luxury hotel, but it is a working testbed for exactly the stuff a deep space ship needs: life support, water recycling, carbon dioxide removal, fire safety, leak management, all in microgravity. Every day on the ISS, systems are pulling carbon dioxide out of the air, removing trace contaminants, keeping humidity in a safe band, routing electrical power, running thermal control loops so the whole thing doesn't freeze on the night side or overheat in sunlight. Every emergency drill, every real ammonia leak scare, every hardware failure they've had to patch in orbit. That's training for what you have to deal with when your crew is not a few hours from home, but hundreds of millions of kilometers away. But here's the catch. The ISS can call home constantly and rely on regular cargo ships. If a filter fails, you fly up a replacement. If a toilet breaks, you ship a new pump. So the obvious next question is, what happens when you can't do that? When every spare part, every litre of water has to be on board from day one? That's where closed-loop life support gets serious. On the ISS today, modern systems recycle up to about 90% of the water. They pull moisture out of the air from sweat and breath. They take urine, process it, and turn it back into clean water. It's not pretty to think about, but it works. Oxygen mostly comes from splitting water into hydrogen and oxygen using electrolysis, with chemical backup system as a safety net. For a Mars-class mission, or anything that really goes beyond the moon, you have to push those loops even tighter. Every kilogram of water you don't have to launch from Earth is a kilogram you can put into extra shielding, bigger habitat volume, or backup electronics. And water is heavy. 1 litre is 1 kilogram, about 2.2 pounds. If you can recycle that same litre thousands of times, the mass savings are enormous. But that also means the gear that does the recycling has to be incredibly reliable. Because if it fails out there, you can't just send up a plumber with a replacement pump. So then you hit the next basic question. If you're taking 4 to 6 people on a roughly 900-day mission, how big does the actual ship need to be just on the living side before you even think about engines? You can't shrink people. Every crew member needs water, food, air, a place to sleep, a place to work, waste processing, medical supplies, exercise equipment, computers, tools. Even with aggressive recycling, you are still looking at several tons of water in the system, tons of dry food and packaging, tanks, filters, spare parts. Add the mass of the habitat structure itself, radiation shielding, insulation, internal walls and fixtures, radiators to dump heat into space, and power systems, solar arrays or nuclear power units. When you add all that up, a realistic living system for a 4 to 6 person Mars mission ends up in the range of something like 30 to 50 metric tons. In plain terms, That's 30,000 to 50,000 kilograms, or 66,000 to 110,000 pounds. If you want a ground analogy, that's like loading 6 to 10 big pickup trucks to the max and saying, okay, all of this as a bundle is just the life support side of the ship. That mass doesn't include the big propulsion stages you need to push it, or the entry and landing hardware for Mars, or the ascent vehicle to get back off the surface. And that's just the minimal version. If you want more comfort, more redundancy, more medical capacity, bigger crew, the numbers grow fast. The more mass you add to keep people safe and sane, the more brutal the rocket equation becomes. So you're constantly asking, can we make this system lighter without making it fragile? It's a design knife edge. Too heavy and you can't launch it affordably, too light and you're gambling with people's lives. So where do you test something like that? When the ISS is close, shielded by Earth's magnetosphere, and depends on regular resupply from below. That's where the gateway concept comes into play. The planned lunar gateway will be an outpost in a special orbit around the Moon, a near-rectilinear halo orbit. It's far beyond low Earth orbit, outside most of Earth's magnetic protection, but still close enough that you can get there in a few days and support it with cargo flights from the Moon program. It's also modular, built from smaller habitat elements that can be launched separately and assembled in space. Gateway is where you can stress test deep space habitats for real. Run the life support with minimal resupply, 90 days at a time, maybe more, see how the systems behave in a harsher radiation environment. Push autonomy, so the onboard computers and the crew can solve problems without waiting for mission control to tell them every step. If Gateway can operate semi-autonomously for months, without major resupply, in deep space, using the same core technology you'd put on a Mars ship, that becomes your proof of concept. In other words, the day Gateway quietly hits a milestone like, we ran this life support system for 120 days without a major failure, with no cargo flights in between. That's a signal. It means the technology is maturing from ISS lab demo to Mars-capable hardware. And this is why habitats and life support are not just boring plumbing details, they directly gate the answer to when. The first crew that truly goes beyond the Moon is not going to sit in a cramped capsule for 2 to 3 years. They're going to live in a miniature city, a closed-loop mini-Earth, with strict mass limits and no outside help. The moment you can keep that little city running safely for around 2 years, with predictable reliability, with repair strategies that don't depend on FedEx from Earth, the question, can we do this, turns into how fast can we fund and assemble this? At that point, the timeline for going beyond the Moon stops being pure science fiction and turns into a project plan. But there's a sting in that progress, because once you admit you need a 30 to 50 ton floating city, plus shielding, plus supplies, you slam right back into the propulsion problem. You're not just pushing a capsule anymore, you're pushing a small space station onto an interplanetary trajectory. So the next hard question is, with chemical rockets already stretched to their limits, what new propulsion tricks are we going to need to cut the travel time, shave down the radiation dose, and make a beyond the Moon mission something a crew can walk away from in one piece? Right now, chemical rockets are just barely good enough to get you to Mars on paper, but not good enough to make the trip short, safe, and repeatable in the real world. So the obvious next question is, can we change the engine itself, not just strap on more tanks? The first big upgrade people are betting on is nuclear thermal propulsion, NTP. Instead of burning fuel and oxidizer together like a normal rocket, you use a nuclear fission reactor as a heat source. You run liquid hydrogen through the reactor core, the reactor heats the hydrogen to extremely high temperatures, the hydrogen blasts out of the nozzle, and that hot gas gives you thrust. The key benefit is performance. In rocket terms, you get something called specific impulse, which is basically how much push you get per kilogram of propellant. Chemical rockets top out around 450 seconds for the very best hydrogen-oxygen engines. NTP can, in theory, go up to something like 900 seconds. That's roughly double. Doubling that number doesn't just look nice on a chart. It means for the same amount of propellant, your spacecraft can change its speed much more. Or for the same mission, you can carry less propellant and more habitat and shielding. For a Mars trip, that translates into shorter travel times, maybe cutting a 6 to 9 month leg down by a significant fraction, and smaller total propellant loads. Shorter trips mean fewer days in deep space radiation, less wear on life support, less psychological strain. Of course, NTP brings its own problems, like running a nuclear reactor in space, managing heat, proving you can do this safely near Earth, and dealing with risk. But purely on physics, an NTP stage bolted to a Mars ship is one of the cleanest ways we have to bend the rocket equation a bit in our favour. So the next thing you should ask is this just theory? Or is anyone actually building and flying one of these? That's where DRACO comes in. DRACO stands for Demonstration Rocket for Agile Cislunar Operations, a joint NASA and DARPA program. The plan is to flight test a nuclear thermal engine in space around the cislunar region, not in some distant future, but as early as the late 2000s. The goal is not a Mars mission straight away. It's to prove that a compact space reactor can heat hydrogen, run a rocket engine, maneuver efficiently between Earth and Moon, and shut down safely. If DRACO hits its performance targets, you suddenly move NTP out of the nice slide in a conference category and into this actually works in space. At that point, it becomes realistic to design a human Mars mission in the 2030s that uses NTP stages, either to speed up the trip, to make the mass budget saner, or both. If DRACO struggles, gets cancelled or underperforms, the timeline stretches because nobody is going to bet a first interplanetary crew on a propulsion system that has never done what it claims in flight. But nuclear thermal is not the only game. There's another technology that looks almost useless at first glance because it's very weak in the short term, but incredibly powerful over months and years. That's solar electric propulsion, SEP. Instead of big chemical burns, SEP engines use electric power, usually from solar panels to accelerate ions, tiny charged particles to very high speeds, far faster than any chemical exhaust. Hall thrusters and ion drives are the classic examples. They've already flown on multiple robotic missions. The exhaust velocity is so high that their specific impulse can reach 1,500 to 3,000 seconds or more. That's several times better than chemical rockets. The trade-off is that SEP thrust is tiny. You don't get that big shove off the pad. You get a gentle, continuous push, millimeters per second added to your speed, day after day. That's terrible for launch and for quick aborts, but it's perfect for cargo. You can attach a solar electric engine to a stack of supplies or a habitat module, slowly spiral it out of Earth orbit, and ease it into a Mars transfer path over months or years. You don't care if the cargo feels a small acceleration, doesn't get bored or sick. This is where a realistic beyond the moon architecture starts to look less like a single heroic launch, and more like a logistics chain. The smart play is hybrid. Use electric propulsion for freight and chemical or nuclear thermal propulsion for people. In that picture, you spend several years before the first crewed mission sending tens or even hundreds of tons of gear on SEP tugs. Habitats, power systems, landing equipment, spare parts, maybe even the return vehicle. They crawl outwards slowly, saving huge amounts of propellant compared to chemical stages, and quietly build up an infrastructure in Mars orbit or on the surface. Then, when the setup is ready and you hit a good launch window, you send the crew in a much faster ship. That ship can be pure chemical, like a cluster of high-performance engines or chemical plus NTP. It burns hard out of Earth orbit, coasts, maybe uses another burn to break into Mars orbit, and the crew spends as little time as possible in deep space. They dock with hardware that's already there, do the mission, then ride another fast leg home. That's split. Slow electric cargo, fast nuclear or chemical crew is one of the main reasons people can say before 2050 with a straight face. It lets you cheat the rocket equation by not forcing one vehicle to do everything. Instead of one gigantic, impossible ship, you have a tug fleet plus a leaner crew vehicle. But you still have to ask, how much do these advanced propulsion systems really matter for the people inside beyond the engineering pride? Every 10% improvement in effective exhaust velocity, or in how much of your mass is useful payload instead of propellant, buys you something concrete. It can shave weeks off each leg of the trip. Or free up tons of mass you can turn into extra shielding, more food, more water, more medical supplies. That's the difference between a crew taking, say, 0.8 sievert of radiation over the mission versus 1.2 sievert. Those numbers may look close, but the health impact is not linear. The higher dose pushes you deeper into a region where cancer risk and other long-term effects become harder to justify. So when you hear about nuclear thermal propulsion or giant electric tugs, don't file that away as just cool tech. These engines directly push on the when question. If NTP and heavy SEP tugs work and scale, they pull the first beyond the moon mission closer in time because the trip gets shorter and safer. If they stall or stay stuck at small scales, we're stuck with long, slow, high-dose chemical missions, and the ethical appetite for sending people on those is much lower. And even if we get these propulsion systems right, there's another layer of difficulty waiting. Once you're months away from Earth, signals take minutes to cross the gap, and you can't fly the ship with someone at a console in Houston telling the crew what to do in real time. So the next question is, when your spacecraft is tens or hundreds of millions of kilometers out, how do you navigate? How do you talk to Earth? And how much can the ship itself think and act without you? How do you fly a ship when every simple question takes 40 minutes to get an answer back from Earth? That's the reality once you go beyond the moon, and it quietly breaks a lot of the habits we've built in spaceflight so far. Start with light time, just the time it takes for a radio signal, travelling at the speed of light, to go from one place to another. Between Earth and the moon, that time is about 1.3 seconds one way. You say something, it gets there in just over a second, they answer. It gets back in just over a second. A round trip is less than 3 seconds. That's basically real-time conversation. You can interrupt, you can react, you can talk almost like you're on a slightly glitchy phone call. Now stretch that out to Mars. Depending on where Earth and Mars are in their orbits, the one-way light time is roughly 3 minutes at best, over 22 millimass at worst. So a simple "are you okay" from mission control and a "yes, we're okay" from the crew can take close to 3/4 of an hour to complete in the worst case. No one is doing real-time call and response in that situation. If something goes wrong on the ship, waiting 20 minutes for Earth to hear you and another 20 minutes to get advice back is not a survival strategy. The crew has to act first and explain later. That delay also kills the kind of constant detailed monitoring and instruction we use today. On the ISS, controllers on the ground watch almost everything. Power flows, oxygen levels, CO2 levels, temperatures, positions. They give the crew step-by-step procedures and can respond quickly when something looks weird. Beyond the moon, that model breaks. Earth can still see the data, but it's always old by the time it arrives, and any response is late by definition. So you rely even more on the Deep Space Network, the DSN, a set of huge radio antennas spread across the globe that already talk to probes beyond Pluto. The DSN can hear incredibly faint signals, but there's a hard limit on bandwidth. By the time your crew is hundreds of millions of kilometers away, you are not streaming multiple HD video feeds like you see from the ISS. You're sending compressed video occasionally, highly compressed telemetry, and carefully selected science data. Every bit has to be worth the time and the power. The control loop flips direction. You're not remotely flying the ship from Houston. You're not joystick driving a rover in real time. Instead, the spacecraft and the crew are flying themselves. Earth is watching, checking trends, sending high-level updates and patches, but not micromanaging. Mission control becomes more like a remote support team, less like a live director. That reality forces a big change on board. The ship itself has to be smart. For a Mars-class mission, the onboard computers cannot just display data and wait for humans to act. They have to plan parts of the trajectory, monitor systems continuously, detect anomalies early, and reconfigure hardware on their own when something drifts out of normal range. Think of it less like a dumb dashboard and more like an AI co-pilot, one that has authority to tweak power routing, change how radiators are used, shift loads between batteries, and adjust life support settings between check-ins from Earth. If a pump starts drawing too much current, the system should notice, isolate it, switch to a backup and alert the crew with a clear diagnosis. If a solar storm warning comes in, the software should already know how to rotate the ship, power down non-critical systems, and guide everyone into the storm shelter. You don't want a human staring at a blinking light for 40 minutes, waiting to hear if mission control thinks this is bad or very bad. Navigation changes too. In low Earth orbit, you can track your position very precisely from the ground, with radar and GPS. Beyond the Moon, you don't have GPS, and ground tracking is slower and less frequent. So the spacecraft needs its own sense of location. That means star trackers that look at the pattern of stars and figure out orientation, sun sensors to know where the sun is, radio ranging to measure distance from Earth by timing signals, and sometimes optical navigation using cameras that measure the apparent position of planets or asteroids against background stars. Robotic deep space missions already do this. They run star trackers, they use onboard navigation algorithms, they correct their own trajectories with small thruster burns. The difference when you add humans is that a navigation glitch is no longer just a lost probe. It might be a crew that misses a critical burn and ends up in the wrong orbit with limited fuel. Suddenly every "you are here" calculation carries human life on top of it. You want that nav stack to be rock solid before anyone rides it. This is why autonomy and comms are not just software details. They push directly on the timeline. You do not want the first humans beyond the Moon to be beta testers for barely proven autonomous fault management. You want them flying on top of systems that have already handled thousands of edge cases on uncrewed missions. You want AI-assisted avionics that have already saved robotic spacecraft from real failures, not just past simulations. Every successful outer-planet mission, every asteroid sample return, every deep space probe that navigates, detects a problem, and recovers without Earth telling it exactly what to do, moves the safe enough date for human deep space flight a little earlier. Each time we send a smarter autopilot, a more autonomous power system, a more reliable star tracker, and see it work, we retire one more unknown, and unknowns are what delay human missions. So now stack this on top of everything else. To go beyond the Moon, you need rockets that beat the rocket equation, habitats that can run like mini-cities for years, radiation and microgravity countermeasures that protect real human bodies, and avionics that can fly and fix themselves with a 20-minute lag to Earth. Even if you get all of that, you still haven't decided what your first beyond the Moon mission actually looks like. Do you just swing past Mars on a free return? Do you stop in orbit? Do you try to land? Or do you pick an easier target like an asteroid first? That's the next level of tension, because the way you answer that question doesn't just set the science goals, it sets the risk level, the mission length, and how soon anyone is willing to sign off on putting real names on that first deep space crew list. So what does the first real Beyond the Moon mission actually look like in practice? Do you go all in and try to land on Mars? Or do you start with something that proves we can just live out there for 500 days without braking? One of the cleanest options on the table is the Mars free return flyby. The idea is simple in concept and brutal in execution. You launch at a very specific time, hit a carefully designed trajectory, and your path carries you out from Earth, past the Moon's orbit, all the way to Mars's orbit. You swing around Mars, bend your orbit with its gravity, and then, without doing a big braking burn, you naturally fall back toward Earth. The orbit is designed so that if your main engine never fires again after the departure burn, you still come home. Mission planners have been studying these free return paths since the 1960s. They show up again and again in crude Mars architecture studies because they give you something very specific, a deep space mission of roughly 500 days that never has to capture into Mars orbit or land on the surface. No atmospheric entry at Mars, no ascent from Mars, no Mars orbit rendezvous. You just commit to living in deep space for well over a year, fly past another planet and come back. Is that risky? Absolutely, because once you're on that trajectory, there's no quick abort. But it's not insane. You avoid some of the hardest delta steps, you avoid building landers and ascent vehicles on the first try, and you focus on the key unknown. Can a crew, a habitat and a life support system really function with no resupply for 500 days and a maximum distance of tens of millions of kilometers from Earth? So then you have to ask, if you're already going that far, why not go a little further and stop in Mars orbit? Why just fly past? Mars orbit missions crank the difficulty up, but the science payoff too. To capture into Mars orbit, you need several kilometers per second of extra delta V compared to a free return. That means more propellant, better propulsion like NTP, or a more complex mission design with error capture, where you dive into the upper atmosphere to slow down. Each option adds risk and mass. The upside is massive. Once you're in orbit, you can stay for weeks or months. You can control drones and rovers with delays of seconds instead of tens of minutes. You can operate sample collection landers, relay high bandwidth data, and map the planet in extreme detail. You turn one crewed mission into the equivalent of dozens of robotic campaigns, because the crew is right there in Mars orbit, making decisions on the spot. From a beyond the moon perspective, a Mars orbit mission hits the goal very clearly. Long time in deep space, very high max distance, no quick way home, but without the extra layer of landing and ascent. You still need a powerful propulsion stack, but you defer the hardest surface operations to a later step. Then there's another option that used to be high on NASA's roadmap. Go to a near-Earth asteroid first. Some of these asteroids, depending on their orbits, are dynamically cheaper to visit than Mars. The total delta V you need can be only a modest bump above what you'd spend on a complicated lunar mission. Mission concepts for crewed asteroid rendezvous were part of the Journey to Mars plans, with several candidate targets studied. The appeal is obvious. Asteroids give you pristine science, untouched rock and metal from the early solar system. There's no big atmosphere to slam into, no deep gravity well to climb out of. Gravity is so low that landing is more like docking with a floating mountain. That's also the tricky part. In microgravity, you have to be careful not to push yourself off the surface. You need anchoring system, tethers, or harpoons to stay attached. But you skip the huge engineering problems of building Mars entry, descent, and ascent vehicles on the first try. From a timeline point of view, an asteroid mission is a strong candidate for an earlier, beyond the moon flight. It proves you can operate a habitat for many months in deep space, you can navigate in heliocentric orbit, you can handle comms delays, and you can do real EVA work away from any planet, while avoiding some of the heaviest delta V demands of Mars orbit and landing. Then there are the more exotic mission designs, the ones that make orbital mechanics people excited and thermal engineers nervous, Venus swingbys and grand tours. Some trajectories use a flyby of Venus to bend your path and shorten the time to Mars or to set up multi-planet sequences. In terms of pure flight dynamics, these can be very efficient, shaving months off total trip time or opening up windows that wouldn't exist otherwise. The price you pay is harsh. A Venus flyby can drag you closer to the Sun, where the sunlight is roughly twice as intense as at Earth's orbit. That means higher thermal loads, hotter spacecraft surfaces, more stress on radiators and cooling systems. The radiation environment is different, the thermal design margins are tighter, and you have to protect the crew not only from deep space cold, but from an intense solar furnace phase as well. For a first human mission beyond the moon, that might be a complexity step too far, but you can see why it's on the table for later. So which of these actually happens first, realistically, when someone finally signs the paper and says, okay, this is the mission that leaves the Earth-Moon system for real? It's probably not a full-surface colony. That image, big domes on Mars, fields of solar panels, dust-covered suits, belongs to a later chapter. The first humans truly beyond the moon are most likely on either a Mars free return flyby or a minimal Mars orbit mission. In both cases, the main achievement is not, we planted a flag. It's, we kept a small group of people alive and functional for hundreds of days in heliocentric deep space with no quick abort. That's the shift in mindset you have to make. The first big leap is about distance and time, not about footsteps in red soil. It's about proving that we can operate a ship, a habitat, and a crew at interplanetary scales without collapsing under radiation, hardware failures, or psychological stress. And that leads straight into the next brutally personal layer of the story. Once you accept that your first Beyond the Moon crew is going to be stuck together in a metal habitat for 500 days or more, millions of kilometers from home, no rescue possible, the key question stops being can the rocket do it, and becomes what does that do to the people on board physically and mentally, and can we keep them stable enough to bring them back in one piece? On the ISS, if something goes really wrong, you always have this safety net in the back of your mind. You're only a few hundred kilometers up, and if you absolutely have to, you can be in a capsule, deorbiting and back on the ground within hours. On a Mars flyby or a deep space mission beyond the Moon, that mental safety net disappears. Once you pass a certain point on the trajectory, there is no abort that gets you home quickly. You are millions of kilometers away, locked into an orbit around the Sun, and no one, anywhere, can physically reach you in time if something goes seriously bad. That no one can rescue us reality is new territory. It's not just a plot line, it's constant background fact that the crew will live with for 500 days or more. Every noise, every warning light, every odd smell lands differently when you know there is no emergency ladder back to Earth. That changes how you sleep, how you argue, how you make decisions. It's not just technical risk, it's psychological load. So the natural question is, do we have any real data on how humans handle being away for that long, even in a safer environment? We do have some experience from year-long missions on the ISS. One American astronaut did 355 days, another 328 days, and Russian cosmonauts have done similar long stretches. They showed that you can work, sleep, and stay more or less mentally stable in microgravity for close to a year, with strong support from the ground. They talk with family, they see live video from Earth, they have regular cargo ships turning up with fresh food and spare parts. And crucially, they know that if something critical fails, a Soyuz or Crew Dragon exists as a lifeboat. That knowledge changes how you handle stress. Deep space strips most of that away. On a Mars-class mission, you will not see Earth out the window as a big blue disk. It will shrink to a bright star. There's no supply ship dropping by every few months. If you run low on something, you ration, you repair, or you do without. The delay in communication means the emotional support from family and psychologists on the ground is slower and less interactive. The crew has to be more self-contained, more honest with each other, and better at conflict resolution, because let's rotate you home next month is not an option. On top of that, staying physically human in a body sense becomes a full-time job. In microgravity, your bones and muscles start checking out if you let them. On the ISS, astronauts already spend more than 2 hours every single day on exercise, treadmills with harnesses pulling them down, resistive exercise devices that simulate weightlifting, stationary bikes. That routine is not about staying fit, it's just about avoiding serious bone loss and muscle atrophy. It's like forcing yourself to run a 10-kilometer, 6-mile equivalent every day just to hold the line. Now scale that to a Mars round trip, you're talking about thousands of hours of mandatory exercise over the mission. If someone skips, gets injured, or the equipment fails and you can't fix it, their bones and muscles will pay the price. That has knock-on effects. Higher fracture risk when you arrive at Mars gravity, weaker hearts, more fatigue, more chance of mistakes at the worst possible moment. The design of the habitat has to put exercising at the same priority level as eating and sleeping, not as an optional if you have time thing. And then, when something medical happens that isn't in the plan, you hit another hard wall. You can't just call a doctor and get live instructions. With 20 to 40 minutes of round-trip delay, telemedicine turns into delayed mentoring. You can send data, video, ultrasound images, lab results, but whatever Earth-based doctors say back comes late. In a real emergency, the crew has to act first, and they have to act with confidence. That means your deep space crew needs real medical autonomy. You're not sending people who did a first aid course, you're sending at least one serious medical specialist, and probably cross-training everyone on basic procedures. You need onboard diagnostic tools, ultrasound machines, compact lab gear to run blood tests, systems to monitor heart rhythms, oxygen saturation, maybe even small imaging systems. You might need 3D printing to manufacture custom splints, tools, or parts for medical devices using materials you already carry. And it's not just injuries or sudden illness. Long missions mean you have to think about infections, dental problems, chronic conditions flaring up, and mental health crises. You need protocols for what happens if someone has a panic attack 15 minutes after you send a message to Earth, or if 2 crew members are locked into a serious conflict halfway through the outbound leg. You need plans for what happens if someone can't continue, physically or mentally, and you still have months to go before you even swing past Mars. All of this is why health and psychology are not just soft issues tacked onto the end of the mission plan. They are a gate. Any credible timeline for sending humans beyond the moon has to prove, not just claim, that we can keep 4 to 6 people physically functional and psychologically stable for 2 to 3 years with minimal resupply. That proof probably comes in stages. Longer ISS missions with more autonomy, then gateway missions in deep space for several months at a time, testing the routines, the medical gear, the group dynamics. Until those countermeasures are tested and validated, with data, every schedule for the first deep space crew is basically a guess pushed by optimism. Rockets, propulsion, and navigation can get you there, but if you can't keep the crew intact in body and mind the whole way, Beyond the Moon stays in the concept art folder. And even if you solve the biology and the psychology, there's still one more brutal layer sitting on top of all of this, because rockets, habitats, propulsion, life support, and long-duration training all cost real money and depend on moods. So the next question is, even if the physics and the medicine line up, who pays for the risk, who signs off on it, and how much are governments and companies actually willing to gamble on the first humans who leave the Earth-Moon system for good? You can build the rockets, the habitats, the engines, and the AI co-pilots, but none of it moves without one more ingredient: money. So the real question becomes, even if we can go beyond the Moon, who is actually going to pay to make it happen, and how fast? NASA's official line is pretty clear. In its Moon to Mars plans, NASA openly talks about sending humans to Mars in the 2030s, not as a one-off stunt, but as the logical next step after Artemis lunar missions, the Gateway Station, and sustained activity on and around the Moon. The idea is a staircase. First prove heavy lift with SLS, deep space operations with Orion, then build and run Gateway, then do multiple landings at the lunar South Pole, and only after that stack those capabilities into a Mars campaign. On paper, it's a straight route from the 2020s Moon to 2030s Mars, but on paper collides with budgets. Look back at Apollo. At its peak in the 1960s, the Apollo program was eating around 4.5% of the entire US federal budget. That's an insane level of national focus. Today, NASA's entire budget is more like 0.4 to 0.5%. That doesn't make Mars impossible, but it changes the tempo. Instead of a crash program that races from first flight to moon landing in a decade, you get a slow, incremental build-up with constant pressure to cut costs and partner internationally or commercially. So every time you hear Mars in the 2030s, you have to silently add, if the funding don't wobble too much over multiple presidential terms. Big crewed exploration jumps only happen when you get this odd alignment of fear, prestige, and cash. Apollo had the Cold War. The Mars program doesn't yet have that same clear trigger. This is where commercial players blow up the old model. SpaceX with Starship is not waiting for a 4.5% federal budget moment. They openly talk about cargo flights to Mars around 2030, with delivered cargo costs on the rough order of $100 million per metric ton to the Martian surface. From an Earth industry point of view, that sounds insane. From an interplanetary mission point of view, that is cheap. That's in the range where a coalition of companies, universities, and maybe a few nations could fund serious precursor missions without a once-in-a-generation government mega program. If Starship or similar systems actually reach that cost and reliability, it changes who gets to play. You could have private consortia sending habitats, power systems, and return vehicles ahead of any government-run crew, building up infrastructure almost like commercial shipping, while NASA and other agencies handle the first crewed flights. That would pull the when date earlier, simply because you're no longer limited to one slow, risk-averse public budget. At the same time, you can't ignore the rest of the world. China and its partners are running their own long game. They've already put taikonauts in orbit, built and occupied the Tiangong space station, and are planning a sequence of robotic and crewed lunar missions. Official documents and public statements have hinted at long-term Mars ambitions as well. The presence of a second major human spaceflight power with its own goals beyond the moon changes the equation. If China starts talking seriously about a crewed Mars mission, or even a major deep space outpost, you suddenly have the same kind of prestige race energy that drove Apollo, just updated for the 21st century. That doesn't automatically mean Mars by 2003X, but it does mean that the first beyond moon mission might be, at least partly, a flex. But even with competitors and commercial shock, there is one more break that didn't exist at Apollo scale, and it's a quiet one: risk tolerance. During Apollo, the accepted risk levels were high. Internal estimates of catastrophic failure probabilities for early moon missions were numbers that today would be impossible to approve for a government program with live video and social media watching. We got lucky, and we also lost crews in other programs later. Challenger in 1986, Columbia in 2003. Those disasters shaped how agencies think. Modern human spaceflight programs are built around much lower acceptable probabilities of losing a crew. That's good for astronauts, but it has a side effect. If you design a Mars mission to Apollo-era risk tolerance, you could probably fly sooner, with more unknowns. If you design it to post-Challenger, post-Columbia standards, you need far more testing, more redundancy, more uncrewed dress rehearsals. That all takes time and money. So when you ask, when will we finally go beyond the moon, you're not just asking about rocket hardware timelines. You're asking, when will governments, agencies and companies decide that the risk of putting a small group of humans in deep space for 500 to 1,000 days is acceptable? That's not a purely technical decision. It's cultural and emotional, and that leads directly into the hardest part of this whole story, the timeline itself. You've seen the tech, the biology, the psychology, the money. Now you have to put all of that together and ask, brutally, when does it all line up enough that a real crew, with real names and families, actually rides a ship that goes beyond the Earth-Moon system and doesn't come back for years? Here's the strange thing about Artemis. It's sold as going back to the moon, but for the people planning Mars and deep space missions, it's really a full dress rehearsal for leaving the Earth-Moon system altogether. Start with Artemis 1. On the surface, it was a clean success. SLS launched, did its burns, and put Orion on a deep space loop. Orion spent 25.5 days beyond low Earth orbit, swung into that distant retrograde orbit around the moon, and came home right on target. Navigation worked, comms worked, power worked, and the capsule hit the atmosphere at around 11 kilometers per second and survived. On the scoreboard, that's a huge win, because it proves the basic stack, SLS plus Orion, can actually do a long, uncrewed deep space mission and bring the capsule back in one piece. But then you look closer at the heat shield data. After splashdown, engineers found more charring and material loss than their models had predicted. Avcoat, the ablative material on the bottom of Orion, had chipped away in over 100 spots. The vehicle stayed safe, but the pattern of erosion wasn't what the simulation said it should be. That's a classic "we passed the test, but the test bit us back" moment. You get confirmation that the overall design works, and at the same time a warning that your understanding of the details is not as tight as you thought. For a short lunar loop, that's acceptable. For a multi-year Mars mission, that kind of surprise is not something you want to cover after you've committed a crew to deep space. So the next step is obvious. Put people in the loop and see what breaks. That's Artemis 2. The plan is to fly 4 astronauts on a roughly 10-day mission, sending Orion on a free return path out past the moon. At its farthest, the spacecraft will swing about 7,600 kilometers, around 4,700 miles, beyond the lunar far side, nudging the human distance record past Apollo 13 for the first time in more than 50 years. But the distance record is almost the least important part. What really matters on Artemis 2 is that life support, comms, guidance, crew procedures and re-entry all get tested under real conditions, with human beings breathing the air, using the systems and sleeping in the seats. Can the ECLSS keep the cabin stable for 10 days? Do the comms links stay solid at maximum range? Does the crew workload make sense, or are they overloaded with checklists? How does the heat shield behave now that we've tweaked the re-entry trajectory? Artemis 2 is the moment where Orion stops being just a successful robot bus and starts being a real human transport we either trust or don't. If that works, the program shifts from "can we do a lap" to "can we live there?" That's where Artemis 3 and 4 come in. Artemis 3 is aimed at the first lunar surface landing since Apollo, currently no earlier than the late 2020s, with astronauts heading down to the moon's south pole. That means docking Orion with a lander, transferring crew, operating on the surface in 16G, dealing with lunar dust, and then climbing back into orbit and coming home. Artemis 4 and later missions are designed to add more pieces, including modules for the gateway, like the International Habitat (IHAB) and logistics elements. Each mission isn't just another flag in the regolith, it's another box checked on the deep space risk list. Long-duration power systems, docking and undocking far from Earth, partial gravity operations, multi-month habitation in an environment that's outside Earth's magnetic shield. With every successful Artemis flight, you build a track record that says, we can handle this level of complexity away from home. Gateway is where that rehearsal turns into something very close to a Mars testbed. Parked in a near rectilinear halo orbit around the Moon, it will sit far outside low Earth orbit in an environment that's closer to interplanetary space in terms of radiation and operations. Crews will live there for weeks to months, running life support semi-autonomously, maintaining systems, handling resupply and visiting vehicles, and doing science and logistics. Multiple spacecraft, Orion, lunar landers, cargo ships, will dock, transfer cargo, refuel, and depart, all far from the comfort zone of LEO. If Gateway can manage long stretches without constant micromanagement from the ground, if its life support can run stably, if crews can handle maintenance and emergencies on site, then you've basically run a scaled-down version of a Mars ship in the actual environment it will see. Deep space, minimal shielding, real comms delays, no quick rescue. That's exactly the kind of evidence any serious agency or company will want before they sign off on putting people in a heliocentric orbit for 500 to 1,000 days. So the real question becomes, how many Artemis missions do we need to fly before anyone responsible says, okay, we're ready to jump? If Artemis 2 flies cleanly with crew, Artemis 3 lands and returns safely, and Artemis 4 and maybe 5 deliver and operate Gateway modules through the 2030s, then by that point you've demonstrated a lot. A heavy lift launcher that works repeatedly, a deep space capsule that can keep a crew alive for weeks, a small station that can run in deep space for months, and a working logistics chain beyond low Earth orbit. That set of proofs, heavy lift reliability, deep space life support for months, complex operations beyond the magnetosphere, is the minimum viable checklist before any cautious space agency or serious private partnership pushes the button on a true multi-year Mars or asteroid campaign. Without it, you're gambling. With it, you're just taking a very expensive, very dangerous step that at least sits on a foundation of real data. And that takes us to the question hanging over this entire story. If Artemis is the rehearsal, if Starship and nuclear propulsion are the tools, and if Gateway is the training ground, then when does all of this converge into an actual date where a real crew leaves the Earth-Moon system and doesn't come back for years? How early could that happen if everything breaks our way? What's the most realistic band given how slowly big programs move? And how late could it slip if anything in tech money goes sideways? Here's the next hard thing you have to pin down. If we're finally going to leave the Earth-Moon system, where do we actually go first? because beyond the moon is not just one place, it's a menu, and each target changes the risk, the timeline in a different way. Mars is the obvious first deep space goal, and also the hardest to ignore. On average, it sits tens to hundreds of millions of kilometers away from Earth. At its absolute best, during a favourable alignment, the gap shrinks to about 54 million kilometers, roughly 33 million miles. At its worst, when Earth and Mars are on opposite sides of the Sun, the distance can go past 400 million kilometers. With current chemical propulsion, you're looking at about 6 to 9 months of travel one way on a standard transfer orbit. Mars itself is not a copy of the Moon with a red filter. It has a thin atmosphere, enough to give you real aerodynamics and real heating during entry, but not thick enough to make landing easy the way Earth's atmosphere helps airplanes and capsules. Surface gravity is about 0.38 g, a bit over a third of Earth's. That's way stronger than the Moon's microgravity field, but still far below what your body evolved for. So landing is harder than the Moon because of the atmosphere, and long-term staying is a giant unknown because of partial gravity. In other words, Mars is the most interesting target and the one that stresses every system you've designed. So then the natural question is, if Mars is the headline destination, is there something easier we can hit first that still counts as truly beyond the Moon? Near-Earth asteroids are the leading candidates for that. Some of them have orbits that bring them close to Earth with relative velocities that are low enough to make the required delta V not much higher than what you need for complex lunar missions. The exact number depends on the asteroid and the launch window, but in some cases, the total speed change you have to buy is only modestly above a moonshot. For a first beyond Moon mission, an asteroid has a few big advantages. You get pristine science, untouched rock and metal, that have been floating around since the early days of the solar system. You can practice deep space navigation, long communication delays, and EVA operations far from Earth. There's no atmosphere to slam into, no deep gravity well to escape. The challenge is microgravity. Landing is more like docking with a floating rubble pile, and you need anchors, harpoons, or tethers to keep the crew from slowly drifting away. But in terms of raw energy and hardware, an asteroid mission strips away some of the hardest pieces of the Mars problem, while still forcing you to live out in heliocentric deep space. Then you have a middle option between asteroid practice run and full Mars landing, and that's Mars orbit only. No landing on the first go, just insertion into orbit and a long stay. The science payoff here is huge. A crew in Mars orbit operating drones, sample return landers, and surface rovers deals with light time delays of seconds to maybe a few tens of seconds, instead of the 5 to 20 minutes you get from Earth. That means they can drive rovers in near real time, make quick decisions, adjust plans based on what they see that day, and coordinate complex tasks. One crewed Mars orbit mission could easily do the work of dozens of separate robotic missions. You could run multiple landers at once, grab samples from many locations, and even pick up cached samples from previous robotic campaigns to bring back to Earth. And you do all of that without committing to the riskiest steps: human entry, descent, landing, and ascent in Mars' tricky atmosphere and partial gravity. For policymakers and engineers, that's a strong argument for an orbit-first architecture. You still check the beyond the moon box and you get massive science returns, while giving yourself more time to mature surface systems. But the target menu is even broader. There are more exotic options that don't involve Mars or asteroids at all. One idea is to park a deep space habitat in a heliocentric orbit, slightly inside or slightly outside Earth's orbit. Basically a space station that circles the Sun instead of Earth. You send a crew there for a year or two as a pure long-duration test. No landings, no planetary gravity wells, just living in deep space, running life support, testing propulsion stages, practicing emergency scenarios, and gathering radiation data. Another option is a human-tended outpost at the Sun-Earth L2 point, about 1.5 million kilometers away, around 930,000 miles. That's the region where we already park observatories like the James Webb Space Telescope. A habitat at L2 would sit well beyond the Moon, in continuous deep space, sharing a neighbourhood with high-value instruments. Crews could go there to service telescopes, upgrade instruments, and test multi-vehicle operations far from low Earth orbit. It's like a halfway house between Earth orbit and true interplanetary missions. So the obvious question is, given all these choices, what's the most plausible sequence, not just technically, but financially? A realistic order looks something like this. First, you build up deep space capability in the Earth-Moon region. Artemis missions, gateway, lunar surface operations, maybe nuclear and electric propulsion tests in cislunar space. That's your training ground. Then, once you've proven your habitats, propulsion and autonomy, you do the first real beyond-the-moon step. Either a Mars free return flyby or a crewed mission to a near-Earth asteroid, possibly followed by a Mars orbit-only mission. From there, if everything works and the appetite for risk holds, you finally move on to Mars surface expeditions. In that chain, beyond the moon happens as soon as step 2. The moment a crew is in a heliocentric orbit, weeks from any chance of quick return, you've crossed the real line. Colonizing Mars, building bases, staying for years, that's step. It's a different era. And that brings you to the tightest part of the whole story, because once you accept that rough sequence, you can't dodge the timeline question anymore. Given the ships we're building, the missions on the books, the tech that's in development, and the commercial noise around all of it, how early could that second step actually happen? What's the most honest middle prediction? And how far into the future does it slip if even a few of the pieces we've talked about start to fail? Now we're at the part you actually care about, dates. When does this stop being a plan on slides and turn into a real ship with a real crew, leaving the Earth-Moon system and not coming back for years? Let's start with the most aggressive path, the commercial everything goes right scenario. SpaceX and Elon Musk have publicly talked about Starship flights to Mars in the second half of the 2020s, starting with uncrewed cargo or even humanoid robots on board. In that picture, you get a series of cargo missions around 2030, testing landings, life support demos, maybe even sending pre-deployed habitats and return vehicles. If Starship becomes reliable, refueling in orbit works, and the cost per launch drops enough to fly often, then human missions in the 2029 to 2031 window are not pure fantasy, they're just extremely optimistic. In that best-case timeline, your first real beyond-the-moon mission could be a Mars orbit or even Mars surface mission in the early 2030s. The crew rides a Starship or a Starship-assisted architecture, does a 6 to 9 month transit, spends time in orbit or on the ground, then comes back on another transfer. That would put humans hundreds of millions of kilometers from Earth less than 10 years from now. It's not likely, but it's physically and technically possible if several big things line up. Starship matures fast, funding stays strong, no major accidents knock the program back, and regulators tolerate the risk. Then you pull back a bit and look at the cautious version, the NASA plus partners scenario. NASA's Moon to Mars roadmap is already structured as a decade-scale build-up. Artemis missions through the 2020s and early 2030s, gateway assembly, multiple lunar landings, long-duration habitation, maybe nuclear thermal propulsion demos like Draco in the cislunar region. In that world, the first crewed Mars mission is sometime in the 2030s, but if you're honest about delays, late 2030s is more plausible than early 2030s. You have to factor in that Artemis has already slipped more than once, hardware takes longer, budgets get squeezed, international partners move at different speeds, validating nuclear or advanced cargo architectures takes real time, so a conservative responsible guess looks like this. Humans go beyond the Earth-Moon system for real, meaning multi-month heliocentric deep space flight in the mid-2030s to early 2040s on a mission that might be a Mars orbit, a Mars flyby, or an asteroid rendezvous. It's slower, but it matches how big government programs usually behave when safety is non-negotiable. Now, you can't ignore the pessimistic branch because history is full of cancelled Mars plans. If Starship underdelivers, if SLS and Orion run into cost or reliability walls, if Artemis gets delayed again and again, or if we have a major accident that kills a crew and triggers a freeze, everything stretches. Layer on top of that global recessions, wars, pandemics, or climate-driven budget shifts, and it's very easy to see deep space crewed missions slipping by a decade or more. We've seen this movie already. Bold Mars architectures laid out in the 1970s, 80s, 90s, 2000s that never happened because money or fear got in the way. In a high-risk averse, low-budget world, a date in the 2050s for the first true Beyond Moon crew is not crazy at all. It's depressing but not unrealistic. So how do you turn all of that into a single answer that isn't just wishful thinking or doom? You cut it into 3 bands. First, the earliest believable window. If Starship or a similar commercial heavy lift system really matures fast, if refueling in orbit becomes routine, if Artemis hits enough of its milestones, and if we avoid major disasters, then late 2000s to early 2000s is the most aggressive slot where a Mars flyby, Mars orbit, or even a minimal surface mission could put humans in heliocentric deep space for many months. That's the everything breaks our way case, not impossible but very demanding. Second, the most realistic band, given how space programs behave, is mid-2030s to early 2040s. That assumes Artemis 2, 3, 4, and maybe 5 fly successfully. Gateway operates for a while, we see multiple Starship-class vehicles fly and land reliably. And at least one advanced propulsion or logistics system like nuclear thermal or large-scale solar electric tugs proves itself. In that world, a cautious NASA-led or international mission, perhaps combined with commercial hardware, sends a crew on a Mars orbit or asteroid mission somewhere between about 2035 and 2045. Third, if things go sideways, technical setbacks, economic shocks, you're looking at before 2050, but probably not much sooner. We keep talking about Mars, we keep flying robots, but the first real deep space crew stays just out of reach, decade after decade as priorities shift and risk tolerance drops. So when you ask, when will humans finally go beyond the moon? In the strict sense we've been using, multi-month heliocentric deep space flight, no quick abort, maximum distance in the tens or hundreds of millions of kilometers, the honest summary is this. Earliest believable window, late 2000s, 20s to early 2000s, 30s, if commercial systems like Starship hit their goals fast. Most realistic band, mid-2030s to early 2040s, if Artemis, Gateway and advanced propulsion mature on the usual slow, steady government timescale. Worst case if we stumble, sometime before 2050, but not much earlier. So your on-camera line can be very simple and very sharp, and you can say it without lying. If nothing catastrophically derails us, someone watching this right now will live to see humans not just loop around the moon, but cruise hundreds of millions of kilometers from Earth in deep space before mid-century, and quite possibly in the 2030s. And that sets up your final move, because once you've given people the dates, you still haven't answered the emotional part. When that first ship finally goes, what will it actually feel like to cross that invisible line? To smash the Apollo distance record into a rounding error, and to watch Earth shrink into a star while you head out into the dark? When we finally go beyond the moon, the first thing that breaks is your sense of scale. On a Mars flyby or orbit mission, the crew won't be a few 100,000 kilometers out, they'll routinely be tens to hundreds of millions of kilometers from Earth. The current human distance record, Apollo 13's roughly 401,000 kilometers, about 249,000 miles, turns into a tiny number, less than 1% of the peak distance on a good Mars trajectory. At some point in cruise, a crew member will pull up the nav display, see distance from Earth, 120 million kilometers, and the Apollo record will be a rounding error on the side of the screen. That change matters. Up to now, every crewed mission has felt like an extreme version of near Earth. Even at the moon, you're still essentially in Earth's backyard. On a deep space Mars transfer, there will be a day when the distance back home clicks past 1 million kilometers, then 10 million, then 100 million, and it just keeps climbing. The numbers get so large that your brain stops connecting them to anything familiar. That's when beyond the moon stops being a phrase and turns into a daily reality, stamped into every status report. The speeds are just as brutal. On a typical Mars transfer with current-style trajectories, your cruise velocity relative to the Sun is around 24 kilometers per second, about 86,000 kilometers per hour, roughly 53,000 miles per hour. The ISS orbits Earth at about 7.8 kilometers per second. So on a Mars ship, you're moving at around 3 times that orbital speed, not for 90 minutes, but for months. Try to picture it in plain terms. A racehorse can hit about 70 kilometers per hour, around 43 miles per hour in a sprint. Your ship is doing over 1,000 times that speed relative to the Sun, and it sustains that for half a year. You burn once to get on that trajectory, and then you're just falling along that path, locked into a regime of energy that no aircraft or rocket on Earth ever experiences for that long. If something goes wrong, you can't stop, you can only adjust the path slightly. The energy is baked in. But the mission isn't just about distance and speed. The real payoff, the thing that justifies the risk and the cost, is what you bring back. A first beyond moon mission that goes into Mars orbit or rendezvous with a near-Earth asteroid isn't just a joyride, it's a science haul on a different level. From Mars orbit, you could support landers that grab samples from carefully chosen sites, cache them, and send them up to meet the orbiting ship. From an asteroid, you can drill into rock that has been untouched for billions of years. In both cases, you're talking about kilograms of pristine material returning to Earth. Not just dust, but curated samples from specific layers, specific minerals and specific environments. Those rocks and atmospheric samples carry records of climate history, solar activity, maybe even chemistry that brushes up against biology. You go from "we flew farther than Apollo" to "we just got the best data on planetary evolution and potential life outside Earth that humanity has ever seen." One well-run deep space mission like that could rewrite sections of planetary science textbooks in a single stroke. Then there's the cultural side, which is easy to underestimate until it happens. Apollo redefined what a world event was with a handful of moonwalks and fuzzy black and white TV. People stopped what they were doing, gathered around screens, and watched humans move in 1/6 G on another world. That was with 3-day trips, short surface stays, and a moon that still looks big and bright in our sky. Now picture a live feed, even if it's low bandwidth and compressed, of a crew in deep space watching Mars change over weeks. At first, it's just a bright dot in the black, then a disk, then a sphere with visible ice caps and clouds growing frame by frame in their window. Light time is measured in minutes, not seconds, so everything you see is already old and everyone on Earth knows that. That kind of footage will twist people's sense of far away permanently. Kids who grow up watching a crew cruise 100 million kilometers from Earth won't think of space as the ISS altitude anymore. Low Earth orbit will look like the curb outside your house compared to the highway. The psychological center of human spaceflight will jump from "we go up and circle Earth" to "we travel between worlds," and once that shift happens, it's almost impossible to walk it back. So how do you close this story without overselling or sugarcoating it? You don't pretend the physics is uncertain, it isn't. We know how to throw ships onto Mars transfers, we know how to build life support, we know how to shield, spin and navigate. We're building SLS, Orion, Starship, Gateway, nuclear demos, electric tugs. The engineering problems are vicious, but they're not magic. We also know the biology risks are real but not instantly fatal. We can quantify radiation doses, bone loss, muscle loss, and we're already testing countermeasures. The real variable is us. Do we decide that it's worth spending the money, grinding through the engineering and accepting a non-zero chance that the first deep space crew might not all make it back? Or do we talk about Mars in press releases, keep orbiting a few hundred kilometers up and let the someday date drift while other crises feel more urgent? We're not asking if humans will go beyond the moon. The physics already works, the hardware is literally being welded, tested and launched right now. The only real question is whether we, as a species, choose to pay the price in money and engineering effort, and in the level of risk we're willing to put on a small crew soon, or whether we stall and push it off to the next generation. Because somewhere between the late 2000s and the 2040s, a real person is going to strap into a real spacecraft, feel that final burn light under them, and know that when the engines cut off, the moon is already in their rear view, and there is no quick way home. On that day, for the first time, humanity will stop being a purely planetary species and start becoming a truly interplanetary one. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.